Thanks a lot. So thank you everybody for attending. Thanks to Nushin for a nice tiny introduction towards this talk. So I'm Johan Peltenburg from Delft University of Technology. I'm going to talk about our framework that we call Fletcher, because it's built on Apache Arrow, and then we had to come up with a name that had something to do with arrows and FPGAs. So the F is for FPGA in the Fletcher part, I don't know, but Fletcher has something to do with arrows, so that's why it's called like that. So we have that out of the way. So let's first give thanks to all the people. Peter mentioned a few already here in our development team. And we have also some PhD students and master students assisting me with a lot of interesting stuff. And we also get some nice support from our advisors, of course, including Peter, and then also from Xilinx and the FitOptivis European project. And also from IBM and Alpha Data for some nice accelerator cards that we test our stuff on. So thanks to all those folks. So the outline for my talk is I'm just first going to talk a little bit about the heterogeneity challenge in big data systems. Then we'll slowly get to Apache Arrow itself. I'll give a very brief introduction on it because it's a pretty massive project by now. And I'll talk about how our framework brings that to FPGA accelerators. I'll show you a little mini tutorial that all of you could do on your laptops almost for most of the steps, until you need some FPGA, of course. And I'll talk a little bit about some future work and ongoing stuff in our lab based on this framework. All right, so contemporary big data systems are very, very heterogeneous. So not only in terms of hardware are they becoming more heterogeneous, but all the software components are also very heterogeneous. So just a little example of one big data framework is TensorFlow and Spark. You run a Python program, it uses NumPy, that's Python bindings on a C core. It interfaces with TensorFlow, that's programmed in CUDA, runs on a GPU, and that runs on top of Spark, which is a Scala Java framework mainly. That runs on a Java virtual machine, and then that abstracts your CPU and I/O, right? So that's a pretty many layers in that stack there, and it's not untypical for big data accelerator, big data analytics systems to have such a varied stack of components. And so some of the technologies that people use, especially very high-level language runtimes, are not necessarily designed to process terabytes of data. And so me as an FPGA accelerator guy, right? If I look at those stacks and I'm trying to find out where's my data in all of this, right? It's like a pretty hard question. And the second question that you could ask is, what does the data look like? Is it usable to me at all when it enters my FPGA? Can I start processing on it already, or do I have to do some other stuff? And it turns out these questions are, they go pretty deep. So by the time you get to the core, like with this onion on the right, you might be crying a little bit, right? So just to give an example, I have a few memory layouts of a string object in different language runtimes on the left. So I have it for a few popular ones, but we could come up with others. And they would all look different, right? So for C++, we have the size of the string and then a pointer to a character buffer, but sometimes it uses an internal character array if the string is not too large. And in Java, it looks different again. I will not go into details too much. Even the encoding is different of the characters, right? And then in Python, it's again different. So for me as an FPGA accelerator guy, when I look at this, it's like, it's not very usable to me, because even if I would load this sort of data structure straight into the FPGA, I see a lot of fields that actually are not very usable to me. What would I have to do with a JVM object header? It's useless data to me. So that's already a little bit of overhead there that, when I load that data into the FPGA, I lose a lot of bandwidth because of that. And also it's not really in a format that helps me a lot, because I have all these, I have to traverse these pointers and I have to pay memory latency and that sort of stuff. Right? For an FPGA guy, I would like to have a stream with the lengths of the strings and another stream with the characters of the strings. For me as an FPGA guy that wants to create some sort of data flow design, that would be much more convenient, right? So it's not so easy to, once you create your FPGA design, to integrate it with all these different language runtimes. And so that makes matters very complicated if you want to accelerate stuff in a big data environment, because people use these very high-level language runtimes. All right, so what you have to do is you have to take that, all these little pieces of memory. You have some collection X in the memory of some process A, for example, and there's a lot of pointers to traverse once you get to the data. And when you want to transport that data to another process, maybe it's an FPGA component, maybe it's another software process or something. Typically, what people have to do is what we call serialization. So we gather all the information we want. We store it in some sort of intermediate format, maybe, or already in the desired format. That's also possible, of course. We put that in an IPC message or in some shared memory, and then we deserialize it back into the language runtime that is the destination of the data. Or maybe we deserialize it into something that the FPGA can use. But this is pretty costly, right? Because we have to iterate over all the objects, but remember, we have a lot of objects because the data is very large. We have to traverse all these object graphs, so depending a little bit on the choices made by wherever the data is coming from, we have to have a lot of traversals, or maybe less traversals, but we have to pay memory latency all the time, right? And we have to make a lot of copies, so we lose bandwidth. And sometimes we also have to reconstruct the objects, like I said. So it's quite costly, and it's a relatively big problem, and many people are working on getting rid of all this overhead. So on accelerators, this can have a very high impact, actually. So if you have some original software process running on your CPU, and you're like, okay, it's a little bit slow, let's accelerate it with whatever, maybe GPU or FPGA. And very often you'll see, okay, I have to, I'm going to create a nice accelerator. It's going to run very, very, very fast. So the accelerator compute time is decreased a lot. But then you still have to do the serialization, right? So that's a completely non-functional component of the total runtime of your accelerated solution. And so it can be very, very substantial. So this is not just copying the data over, it's also reordering it and putting it in the right place. So what you would like, even if you had to copy to your accelerator, you just like to have just that copy and then do the computation and copy the result back. And you don't really want to reshuffle all the bytes in different positions and traverse all the pointers and that sort of stuff. So in 2016, I think, we did, or 2017, we did some preliminary measurements on one of the language runtimes. A very popular runtime framework is the OpenJDK in big data world, because Java runs on it and Scala and stuff. Right, and we measured on Power 8 for specific, for all sorts of object graphs, actually, like how fast can we serialize that? And when we look at the performance of that, it's actually quite low. So we could only do it like in a safe way. So the top two ones are basically cheating, and no sane software developer would ever use them because they're very unsafe. So if you do it in a safer way, we couldn't really get above close to a gigabyte per second, even if we increase the number of threads a lot. So that's not the kind of bandwidth that you have for your accelerator itself, right? Because now we're getting OpenCAPI, for example. We're going to have 25 gigabytes per second. But yeah, even though that bandwidth is very high, if we still have to do all this serialization, it's just we're not going to be able to leverage all of that bandwidth. So not only us, but, oh wait, okay, so I'm just going to show you like what happens if you don't have to do that serialization. We did a little experiment. It's also a sneak preview because we actually used Fletcher to implement all of this eventually. So we did regular expression matching. We have a whole bunch of strings. We used about a gigabyte of strings, like this, and then we have a regular expression, and then we want to match the strings to that expression. And FPGAs turn out to be pretty good at that, or hardware in general, right? So it's something that we can accelerate very well. But yeah, I mean, we just saw what the strings look like in a software runtime, and that's not very, very convenient for us. So we're going to see what happened, right? we did regular expression matching on a gigabyte of tweet-like strings, so they're going to be, I don't know what's the max characters. It's like 240 now, right? Something like that. And so the bottom graph is actually on a Power 9 system, and we used CAPI SNAP to do that. And so here you can see the runtime components, right? So this is the CPU compute. So sometimes we do it in 3 languages. We do it in software only, with all the threads enabled. You can see it takes about, in C++ is the fastest, it takes about 3 seconds. And then for Python and Java, they're really slow. So Java is it's kind of fast, so compared to Python still. So that was like 7 or something, and then Python was about 10 seconds. And then when we did this in FPGA, just the compute part, so not the data transfer part or serialization, we can do it in like a few milliseconds, right? A bunch of milliseconds. So that's really fast. We have a nice accelerator. The computational performance is really good. But now we have to get those strings from a C++ runtime environment, or a Python runtime environment, or a Java runtime environment into the FPGA. So we just saw, okay, the format is not very usable. We want to turn it into streams. So we have to serialize it, right? And now you can see the serialization component here. And here it still makes sense to do it, because in total the runtime is going to be less, even though we have to serialize. But in some cases, the serialization overhead is so large that it doesn't even make sense anymore to use that accelerator, just because the data format is, it takes too much time to reorder it and to serialize it into something usable. All right, so what can we do? Okay, so we have to overcome the serialization bottleneck for the reasons I just showed in the example, right? So these in-memory formats, it's very hard to tell people to change them, right? Because they're determined by a lot of factors. So they can be determined by the programming language themselves, and especially the standard libraries and the runtime system design choices dictate that they're going to look like this. And very often the programmers themselves don't even have to think about them anymore in these very highly abstracted languages. But also the algorithms can, of course, dictate what the data looks like in memory, and the programmers themselves, they could do something about it if they wanted to. So we see that there's increased heterogeneity in big data systems, right? We have to do more inter-process communication, so we have more serialization overhead. So a lot of very smart and experienced folks thought about that, and they said, well, what if this data is in a standardized format? So we're not going to let the language runtimes dictate anymore what the data looks like in memory. We're going to decide that for ourselves, right? And we're going to standardize that. And in every language that we use, we just expose access to that data through some library, rather than using the language constructs themselves, or the language library constructs themselves. And then we're going to try to make that as contiguous as possible. So whenever we transfer it, even if we have to transfer it, we can do it using large bursts. We prevent a lot of pointer chasing and misalignment issues. So and those folks come up with Apache Arrow, which is a great project. So normally you would have like your big data system here with lots of components. So for example, you'd have a Python tool or something. You want to make that work with something like Apache Spark. And you had to do all this serialization and deserialization back into the Python tool and make copies, right? So they thought, okay, it would be much nicer to have this shared memory. We specify the format of the data in memory, and we can just share the data set across different processes through the libraries. And so the Python tool and Apache, and for example, an Apache Spark application, all of them could consume that data in the same format without moving the data at all or making any copies. So of course that's a great idea. They call this zero copy inter-process communication. And so they've chosen that to be a columnar format because it's very hardware friendly. In many cases, that helps a lot. It's better for some algorithms, it's worse for others. Sometimes you benefit more from a row-based format. But this is the choice that they made. And we thought that's a very good idea. So our idea was to, add a little thing, which is not little anymore now, that would, give that benefit also to FPGA accelerators. So this project is more like under the hood of a lot of other projects. So a lot of big data analytics frameworks like Spark and Dask, Parquet and Pandas, they are all starting to see integration with Apache Arrow a lot nowadays. So once all those projects have shifted to use this method, any FPGA accelerator could also unlock access to that platform immediately. So what does it look like, the Arrow format? I'm just going to show a very simple one. So there's a bunch of terminology that they use in Arrow, right? So we want to store tabular data sets. So here's a little table. And the types of the data in the table are described through a schema. And here's an example of a schema. So we just say, okay, in column A we have floats. In column B we have something like a list of characters, which is basically a string, right? You can have structs, but you can have many other more advanced types like dictionaries and sparse and dense unions. But I'm not going to go into that now. And then, so this data set, once it's there in memory, it's called according to the schema, it's called a record badge, right? So the record badge physically has a bunch of arrays, and arrays are, again, a combination of arrow buffers that hold all sorts of, data, and the combination of the buffers is gonna cause the record badge to, to contain the types that you define through the schema. Right, so here, for example, for this column of floating point values, we have two buffers. Why? Because, okay, you can also have something like nullable, you can have null values and that sort of stuff. So all of that, all of those things are in the format. And the string looks different, so it has an offset buffer. For every string, it points somewhere in the values buffer where that string starts. And so this is highly contiguous if you would compare that to something like a C++ string or a Python string or something that is more spread out over throughout memory. Okay, so all these things we have to also, when we want to take this to FPGA, we also have to support all these different things, right? So it turns out Arrow is very hardware friendly. Well, turns out, because it's been designed like that, of course. It's clearly specified in memory format. We cannot say this about many of the data formats that we can find in language runtimes. For example, in Java, there's no specification on how the data must look like in memory. It only specifies what sort of information should be there, partially. So that's a big advantage. So if you know the schema, you know exactly where the data is, so we can do all the pointer arithmetic to find it. It's highly contiguous in columnar, so whenever we want to use it in the FPGA, because it's so contiguous, we can easily stream it in, right? It's very useful for maps, reductions, and filters. It's also parallel accessible, so it uses, for example, the offsets rather than lengths to figure out where strings are, like we just saw. And so our question was, can we generate easy-to-use and high-throughput hardware interfaces for this format automatically? And of course, the answer was yes. Right? That's why we're here. Okay, so what you usually see as an accelerator developer on FPGA, usually you interface with a memory directly through a byte address and you get a buzzword, right? And this is very wide nowadays, 512 bits on, for example, Snap, OpenPOWER SNAP, right? And then you have to do a lot of work to make this really fast and do the thing you want, right? So that's a lot of work, and then you can get to the computational part. So our idea with Fletcher was that let's just generate the interface, create the streams that we, at the beginning of the talk, saw that we would like to get if we talk about a string or something. And rather than giving byte addresses, we just want to give table indices to the interface, because then we don't have to do the pointer arithmetic ourselves. And then we get the streams of data back. So this, for us, means, that's easy to use, right? Because it's much easier than working with bytes. Now we actually get the types of streams that we'd like to see based on the schema and the types of the fields in the schema. And we also wanted to make it high throughput, so we wanted to make sure that we do get that 25 gigabytes per second or something now. And so we shouldn't really be limited by, if we get a stream of characters, if we would deliver you one character per cycle, that would not be a very high throughput. So all the streams that you get from Fletcher, well, almost all of them, you can also have multiple elements per cycle in those streams. So it's quite involved to create this, of course. And so eventually we came up with the whole Fletcher architecture like this. So what you do as a developer during compilation time, the top of this figure, is you start with the arrow schema, you throw this in a thing that I will explain later, which is our interface generation tool. Then you get an HDL template, or work is being done on HLS templates, and you get interface sources. So the schema is going to dictate to you, okay, what's the interface of my kernel, accelerator kernel? Then you still have to implement that. We don't do that for you. You can use whatever tools you want, whatever techniques you're used to, as long as you adhere to the interface. And then you synthesize, place, and route, of course. And then you get your FPGA design with the hardware accelerator function there, or your hardware kernel. So during runtime, all you have to do is you have to use the Apache Arrow libraries. The first time, as soon as you load the data from whatever source, maybe disk or over the network, through the Apache Arrow libraries, you store it in the memory in that format. So now it's an arrow table here. And then, we've fully automated transfer of that arrow table to the FPGA, and all you have to do is give a table index, and the data streams roll out, right? And they roll out fast. Now, if you don't use CAPI, but you don't have some sort of shared memory system, then you still have to copy this table on board to the accelerator card, right? But if you use CAPI, you can directly, pull it into the accelerator kernel. Now, our runtime libraries take care of that. All right, so this is the general overview of the framework. And so I'm just going to go really fast. I don't know, how are we in time? Pretty good? Okay. Okay, so not as fast then. Less fast, I'm going to go over all the other components in the framework. So we build it up from the ground. We don't use any vendor IP, so we had to do a lot of work. It should be able to run on any FPGA platform, basically. So we based the whole architecture on a pretty extensive library with streaming primitives, and then we use all those primitive components to build up what we call buffer readers and writers to read from the arrow buffers, or to write to the arrow buffers. So combining those buffers we just saw in the record batch, by combining buffers you turn them into arrow arrays, right? So they're not C-like arrays, they can hold much more complex data types. So the combination of buffer readers and writers turns into an array reader and writer. And that is generated through pure HDL up to this point. And then it became a little bit more complex. So to support full tables, like the record batches in Arrow, right? We have to combine these array readers and writers, and we had to make some special tools for that, because the HDL is just too limited for that. And then finally, you have some sort of what we call a mantle. It's just a wrapper around everything that also instantiates the full bus infrastructure that's also generated based on the schema. All right, so we started with streaming primitives. Now, sorry. FPGA acceleration is already a bit of a niche, of course, in big data analytics. We're sort of the new guys, of course. So we thought it would be, most attractive for people to start working with a framework that we build if it's fully free and open source. So we try to do as much of the things that we do with open source tools, including simulation. And so we don't use any IP, because there's a lot of IP that can do these kinds of things. But of course, that's a very steep, entry curve for people. So these, you can use these in any FPGA design, not only in our design, right? So we published this library as well. I'm not going to go over all the components, but they can do a lot of advanced stuff with the streams to make sure that we can maximize the throughput, that we can get multiple elements per cycle and stuff like that. So we use all these components, and then we combine them into these buffer readers, right? So this is a buffer reader for a values buffer. So for example, a C-like array. It does all the pointer arithmetic for you to figure out where is the data and to align it properly, and it reshapes the stream into multiple elements per cycle streams according to your configuration. And eventually you get a stream out of this. But this might not yet be a usable stream for you because it just reads an arrow buffer, and that's not like, let's say, that might not be the data, the same format of the data as you would expect from the schema. So sometimes we have to combine them, right? For example, if a buffer reader would have to read the offsets of strings, we want to give you lengths, right? So for an offsets buffer, we have a slightly different buffer reader, and then the output is lengths, but it also generates a command for the values buffer because we saw that the offsets point to somewhere in the values buffer where the string starts, and it has to start reading from there. So sometimes they're combined a little bit. We also have them for writers, but in the end, combining all the components and having a few different configurations, we were able to support reading arrow buffers. All right. So then onto the next arrow artifact, which is the arrays, right? So by combining all these buffer readers, I'm not going to show the writers for the sake of time, but by combining all the buffer readers, we can support all the different arrow types, right? We can support strings by combining an offsets and a values buffer, like we just saw. We can support nullable floats, for example, by combining a buffer reader to read the values and a buffer reader for the other buffer that says if a value is valid or not. And then we can do structs, and we could do more, but I'm not going to show those. Right? So combining all the buffer readers turns it into ArrayReaders. And so now we can support arrow arrays, right? So we passed the configuration of this architecture as a string in HDL, and that does seek the limits of synthesis tools we noticed. So up to this level of abstraction, yeah, you get some recursive components and that sort of stuff, and then sometimes the tools say, okay, sorry, now I'm going to crash, or they're going to say, sorry, but it's too recursive for me, or something. The depth is too deep, for example. So up to this point of abstraction, we decided, okay, we need something else, which I'm going to show you later. So we wanted to test a lot of configuration strings, of course, because we can have a lot of crazy arrow field types. For example, you could have a list of a structure of a list and an integer, and then inside that inner list, you could have a structure of an integer and a string or something. So the craziest data types you could come up with, of course, there's an infinite amount you could generate. So we decided to, test over 10,000 field types, but just generating random field types, with decreasing complexity on every level. And so it turns out that it's a pretty good test to, test all your components. So we could verify, and then we were sure, okay, now we really support arrow arrays, with not all the types yet, but most of them. So then, like I said, it was really challenging to get everything to synthesize, and actually, what you also want is you want syntactically pleasing interfaces for your kernel. And there's not a nice way to rename ports in HDL itself. Like where you could say, oh, I'm just going to rename my port using some HDL itself. Right, so we had to come up with something better and for that, because we want to group array readers and writers into record batch readers and writers. Right, we want to have the stream names to correspond to schema fields. Synthesizable HDL was too limited, like I said. And also, we wanted to generate the kernel templates, of course. We wanted to include some simulation and platform integration. So in the end, we created a tool called Fletchgen. This is the command line tool that I will show you later. All right. So after we created this tool, it's just unpublished work. Maybe at some point we will put something out there. But it's all open source, you can check it out. Right now we also support record batches. Okay, so great, we're done, right? We support all of Arrow and FPGA now. Right, so there's another component, of course, because during runtime you also want to have that easy integration for programmers, for software programmer. And so there's a pretty big stack that, it starts with a Python application, and that can interface with a Fletcher Python runtime. So for C++, we have a C++ runtime, and if we support more languages, of course, for whatever language we could have runtime for that language. And that gives you some control, that allows you to do some control flow with the FPGA to access the control path through the FPGA. That all comes together in a C API, and and then you get platform support on the hardware side. So we support AWS EC2F1. It's a bit older, the support for that, but our current version does support the latest version of Snap. So that's more interesting for people that are using OpenPOWER. And you could add your own platform to Fletcher. You just shoot us a pull request. Then there's a lot of platform-specific stuff, but in the end, if you have an AXI4 light interface to set some registers, and if you have an AXI4 full interface for the memory access, then we can connect to your platform. Right, so the nice thing about this is that, if you're lucky, you can create one accelerator and then connect it to any of these languages, right? So that's a big advantage, because we're using Arrow as a standardized format, and Arrow has support for way more languages than we support already. All right. So just to show you how easy it is now, might get easier later. Just a little mini tutorial, like our Hello World example. It's a relatively trivial example. It just sums a column of integers. So here we have some integers. We have a really easy record batch. There's only one array. There's just some integers here, and then we just want to sum it and get this result out. Yeah, of course, this is not a real, good example for a big data application where you would have way more complex types and more arrays and way more record batches at the same time, inputs and outputs. But we just want to show you like the tool chain, right? So not necessarily something that's very useful, but just to get to know the tool chain. So this tutorial is available on GitHub. You can just go to our GitHub page and then see exactly the same stuff that I'm going to tell you now. And it works on your laptop up to step 4 or something. So the first step is we have to create an arrow schema. And you can do that in many ways. This is an example how you can do it in Python, because that's just the shortest thing we support right now. You just import PyArrow, that's the Python arrow library. We have to define a field for our schema, right? So we just saw that there's a number array, so we call that number, and then it's an int64 type. We don't make it nullable, so all the values are always valid. Right, and then we throw that field, we throw that into a new schema that we just call schema. And then we have to add some specific metadata for Fletcher to make this, for it to be able to generate hardware from the schema. So because schemas don't have names or something in Arrow, and we're going to generate hardware interfaces that need names, right? So we have to add a name, and we also have to tell Fletcher if it has to read or write to a record batch that you create from the schema. So you add the metadata and you're done. You just have to save it to a file, and then this is how it works for Python, right? It's pretty short. Now what you can do, optionally for simulation, you could also put data in a record batch based on the schema. So here the values that I showed for step 1 are here, 1, -3, etc. Right? So we create a little PyArrow array with these values. Then we put that in a record batch according to the schema. So PyArrow is going to check if that data actually fits with the schema. And then we're just going to create a record batch out of that with 2 lines of Python. We just write that to a file. And the nice thing is that Fletcher can take this record batch and it can generate a simulation model for you. And it will, if everything works correctly on the output stream of your going to your kernel, you will see this data appear. So it's really nice because then you can do some functional testing in simulation. Now we use this tool, Fletchgen, right? So it has some parameters. Looks a bit boring, of course. So it's just a kernel name, the record batch input file that we just created, an output file that's the memory model for our simulator. You can do the design, you can set the design output languages. So we currently support VHDL. I know I'm in the US, so sorry for that. But that should be, if you feel free to add a Verilog backend. But we also have this dot backend that generates a graphical view of the whole design for you. So that's kind of nice for documentation purposes. And we also give this flag to say, okay, we want to have a simulation top level, right? So this is the kind of, this is actually this design for the tutorial that you get a dot graph, like I said. So that's just a visual representation of all the streams in the design. So that's kind of nice, you know. It can do much, we can do much larger designs than to look like this. So I don't know how clear that is anymore. But there's some options there to make it simpler, look simpler or more complicated, or to hide some complicated stuff. All right, so after we've done that, we get all this VHDL code, right? We're gonna look at that because we don't want to cry. So and then you implement the kernel. So you start from the template, you get, in this case, a VHDL template, right? And you can use your favorite tools. You can use custom HDL, or Vivado HLS, we have integration in progress, or anything else. As long as you adhere to the specification of how to use our streams, which is like AXI streams. And then you have some, so these are the interfaces that you will see on your kernel. In AXI 4 Lite for MMIO registers, because you always want to set some constants or whatever and control your kernel. And then you get a command stream towards the generated interface that Fletcher built for you. So you can issue a command, like I want to get all the strings from this range, or I want to get, in this case, all the integers in the record batch or something. And then you get the data stream back. And then you can simulate the design. So we built a little tool because, you know, we have a guy that is very good at building very nice tools. And so with one line of, one command line command, we can actually start simulating already, right? So most of the work is in implementing the kernel still, but at least now we have an interface that's very usable. So we just give the paths to the hardware libraries, and we say we want to use GHDL. This is a free and open source simulator, so you don't even need any vendor tools up to this point. It doesn't really have, you can get waveforms, but it's not integrated with this tool itself. But you could also do like QuestaSim or vSim or something, and then you would get this visual representation of your waveforms. For GHDL, you just get this output. All right, so and then you say, what do you want to simulate, right? So this is the simulation top level that Fletchgen generated automatically for you. That took you less than a second. So then you can run the simulation, and you can see here in the waveform, it's more interesting, I think, than this part. So in the waveform for QuestaSim, for example, you can actually see that, you know, I called my record batch example batch. I called my array number, right? So I can see the same identifiers that I used in my arrow schema here in the hardware. And I actually see that data that I put in the record batch in Python. I see that appearing here in simulation. And so, you know, this gets summed up in this kernel, and the answer is -6. So that works pretty well. So up to this point, so step 5, you can do everything on your laptop without any vendor tools. So then if you really want to run it on a platform, and I can recommend CAPI SNAP, because writing host-side software, you know, the hardware-software code design is really nice on Snap, right? You can write the same software as you for your simulation as you write for your actual hardware runtime. So this is an example of what you have to do on the software side, right? So you import our in Python again, right? You can import PyFletcher, which is our Python library for this project. And you don't have to do a lot of things. This might already, for Python programmers, be relatively low level, but you could abstract that a little bit more. You just have to create initialize the platform. In our case, that's going to be Snap, right? And then you create a context for your record batch to live in the memory of that is accessible to the FPGA. You enable the context. And that means that from that point onwards, the record batches, all your data is going to be available to your FPGA kernel. And then you can control the kernel by creating a kernel on top of that context, and you just start it and you wait for it to finish. And if you're lucky, of course, the answer for this example, -6, is going to roll out. And then eventually you can target the platform, right? So we have support for OpenPOWER CAPI SNAP. And then for this platform, this context enable that we just saw on the previous slide, let me show it to you one more time. This is when actually normally there's going to be some data transfer. So we're going to transfer all the arrow buffers to the onboard memory of the FPGA accelerator card. But actually for Snap, of course, because it's using CAPI, we don't have to do anything. We just pass a few addresses, and then the FPGA can access the buffers on those addresses. And and like I said, there's excellent hardware-software co-simulation. Actually, we can get pretty high throughput. For CAPI 2.0, we get, for example, 11 gig. Yeah, this figure is wrong. So it has to be 10 gigabytes per second for an example where we did reading strings, for example. That's pretty high throughput. Also for writing strings, we could get like 10 gigabytes per second. Well, we already had this working for CAPI 1.0, so a very nice thing that we saw was when we switched to CAPI 2.0, that was pretty seamless. We didn't have to do anything, just tell Snap that we wanted to use CAPI 2.0. So we hope this will be the same for OpenCAPI. Gotta look at the Snap team here. Actually, this hello world example that I just showed you, you can run it on Nimbix. So if you want to do this, please come talk to me after the talk. Then we can maybe talk about how we can collaborate on that. Yeah, we also support this platform, but the support is a bit old. So there's a lot of spin-off projects in our group based on this framework. You have a whole bunch of future work coming up. So I just want to talk about the spin-off projects. So it's a continued development effort in our group, especially Matthias, who's sitting over there, is working hard on that. And we have a few master students. So Lars Weitemans, he worked on dynamic arrow buffers in hardware. So especially for the write path, so if you're writing data into an arrow data structure in memory, you sometimes want to have dynamic buffers, right? You want to be able to resize them as you go because you don't know what their eventual size is going to be. For example, if you have some filter operation or something that Aaron is going to talk about later today, you don't know what the actual buffer size has to be later. So you need some sort of support for that in hardware. So Lars worked on that. I'll show you on the next slide. We have another Lars who worked on a Parquet Arrow decoder and decompressor. So we're going to get some data maybe from a file that flows through the FPGA. It doesn't even hit memory. And then you're actually decompressing that file and decoding that file into an arrow in-memory data structure on the fly. And you might even want to combine it with filtering. But I think Aaron will say some more things about that later. All right, so yeah, we can do all sorts of interesting things with the framework that we built. So we want to do runtime profiling of the data streams, and then we want to automatically improve the generated interface, while you're running it. So your cluster with FPGA is running, and it's going to get better. You don't even have to do anything. So this is an image of what Lars Weitemans is doing on dynamic arrow buffers in hardware. So he's really working on, this is what it looks like for CAPI. So you have the host RAM, the PSL, the interconnect, and then your ArrayReaders and writers. Here it's called column reader writer. And so he's going to add a virtualization and memory virtual layer to that. 3 more minutes. Okay, good. So more interesting work. This is the work I was talking about. So Parquet is an in-memory, disk format for big data. And so Lars is going to work on decoding that. He built a whole nice hardware structure. I think his master thesis will pop up in our university repository very soon. And so you could read all about that. So a summary, big data systems are getting increasingly heterogeneous. So many different tools and many different technologies, and we need some solutions for that, right? To make the inter-process communication contain less overhead. So the folks at Apache Arrow have done a great job to do that, right? One in-memory format for any component, and then we do inter-process communication through shared memory. Now Fletcher enables you to use that standardized format and generate high throughput, easy to use hardware interfaces for FPGA. And then that paves the way for more efficient FPGA accelerator integration with any of the supported software languages. So this is the link to the to the repository, but if you just type Fletcher FPGA or something in Google, you'll also find it. And here are the references and some example projects and existing applications that we did with this framework. So thank you very much for your attention.
Have you seen any limitations or sensitivities of the size of the data set going?
So the question is if I've seen any limitations to the size of the data set coming in. So actually, if the size of the data set is small, yeah, then we see some limitations because, yeah, there is still some latency in doing everything. We haven't really optimized for latency or something like that. So if you have many small record batches or something, that wouldn't work too well. But in general, the bigger the data sets, the better. Yeah.
And of course, the bigger, the CAPI versus.
Yeah, that's also a thing, right? So yeah, so an advantage of CAPI is, we don't have to make a copy at all, right? We don't have to, and we also don't have to use pin memory. So that could be a solution for other platforms, but some people don't like that for specific reasons, of course. Yeah.
Yeah, question. So most big data is actually very sparse, has nans and missing values. So do you optimize for the content inside the data sets? You were doing the optimizations for sparse data.
Okay, so the question is if there's any optimization for sparse data, right? So this is not something that we have to take care of. This is already taken care of, I think, in the Apache Arrow in-memory format itself, right? Because it has these, any field type is nullable. And so it doesn't take up any storage space if there's missing data, right? It only takes up 1 bit of storage space in a validity buffer. So I don't know if that answers your question or if you... Sorry?
We can talk offline.
Okay, yeah, sure, okay.
No, then thank you, speaker, again.
Thanks.